Hello and welcome to the series that I've been recording in Introduction to AI. We're up to topic 9. We're talking about multi-agent decision making. So, spoiler, the name gives it away. It's about whenever more than one agent is making a decision in an environment. We talked about that briefly early on. So, when we talk about multi-agent environments, so what are their properties? This is a relatively advanced topic. Multiple courses offered on this one topic alone at a graduate level. So bear with me as I skim across the top, right? It is relevant to real world scenarios because think of it, the world in which these agents interact may be a real world to a large extent. And it may be a social media world because a lot of those bots out there are probably very close to agents in the way that they function, and largely speaking, they are. So it is relevant to real world scenarios, and it requires understanding of many domains. We'll go over some of this in a very high level. Bear with me again, just skimming the top. So when we talk about multi-agent systems, how they interact with other things, you can see there is a intersection of a great many areas, everything from object-oriented programming, economic theory, decision making, artificial intelligence, psychology, sociology, distributed systems. Some of those are pretty intuitive. Economic theory, you might find that interesting, right? Also, whenever we talk about decision theory, that's where we're pulling from the rationality concept. And apologies, I hit the space bar. Distributed systems very much is related because oftentimes they're the world in which these things interact. The environment may actually span multiple locales, so there is a distributed nature to this. Not everything's running on the same computer, so to speak. So how many decision makers are involved? If we're talking about one decision maker, not all that interesting, right? That's an environment where you've got one agent that makes decisions and you've got others that maybe don't. There may actually also be a benevolent agent assumption. That is that the agents do what they are told, and they're there for good reasons. Agents must work together to achieve the decided actions. So if there's a single decision maker, there could be multiple agents. It's just that one of them is making the decisions. The decision maker must be able to do multi-effort planning, so concurrent planning, if you've got a single thing making the decisions. When you have multiple decision makers, it's an interesting problem at that point, right? Because you've got counterparts, agents with their own plans and execution plans, right? And there's also hopefully aligned goals where they have common goals that are coordinated to work together. There may also, though, be personal goals. That's where an agent has the right to do what is right for themselves. It could be that there's no overlap between the personal goals and the common goals, so it's zero sum. Uses of strategic decision making, game theory. You may end up wanting to do things inside of agent design to analyze possible decisions and utilities, mechanism design to define the rules of the environment, cooperative game of binding agreements between agents to work together for a time, and then non-cooperative game where there's no agreement to work together at all. Whenever you're doing multi-agent planning, it's obviously this is a complex topic. It's got to be interleaved execution. The order in which the agent's execution plan is preserved does not handle true concurrency. So different, not just CPUs, but different computers, different could be in different data centers even, or different regions of the world. There is true concurrency. And so you must use some sort of a partially ordered plan. And you need to do synchronization ever so often. You probably will need some sort of global clock, some way that ordering can be determined, and making sure that you're bringing, but you may even want to use lockstep execution, although that's going to likely be problematic. When you think about non-competitive or cooperative game theory, it all comes down to strategy, and it's a deterministic policy. It's going to be driven by inputs. You may have mixed strategy that's going to be random inputs and random actions. Um, so you may have a deterministic policy plus some random events where you go off and do things that are truly unplanned. There may be a strategy strongly dominates if the approach always gives the best outcome. So we've heard these words before: strongly dominate, weakly dominates. If at least one part of it is better, right, and others no worse. If all players choose a dominant strategy equilibrium, no reason to do something different, right? So basically, they may all reach something that is working reasonably well. They may also reach Nash equilibrium, where no one change can change strategy and benefit. So it has to be a collaborative or coordinated set of changes. There's also a concept of what's best for the economy or the entire society of agents versus one player, one individual agent. So when you deal with social welfare, you talk about what's best for everyone. Pareto optimality is best outcome for all players without improving one at the cost of another. So that would be an ideal thing where everybody gets the best outcome, but not at the expense of another. Utilitarian social welfare is overall measure of how good an outcome is. Interestingly enough, this same topic will come up in AI discussions as well around ethics. In general, you oftentimes have the discussion around do you weigh the good of all? Do you have some way of coming up with a utilitarian societal welfare and so on? I think I have a timer on here. So cooperative game theory, basic idea is that you may have a group of players that are collaboration, and there may be a collaboration where all players are all working together. Imputation, total payout and reward for a coalition. Sorry, I'm blanking on that word for a minute. Individual rationality, a player should earn at least what they would have by working alone. So typo there. At least should earn. Fix that later. So anyway, so there's lots of different approaches whenever you're dealing with the rules that may go into a set of groups of players working together. And you may have a coalition that gets together where everybody plays along, and it may be that it's just that some do, and only if it's making everything better for all. When we make collective decisions, you have a contract of some sort that you're going to work out. And its contract net protocol is a well-established way of addressing multiple agents. You recognize the problem, announce it, take bids, and then award to an agent. And so this is something that's been around for some time over networks of I have a problem, everybody tell everybody about it. They make some sort of proposals. I award to one of them. Or I may get bids afterwards, and then I do the awards. It's awful. Oh, it's going clockwise. Other approaches, you may auction off scarce resources, bargain amongst the agents, may hold elections and vote, may act to avoid conflict, and so on. I'm reminded of a book, Rules of Encounter, I read back a long time ago in the early 90s that dealt with just this topic. Probably still in print, probably grossly outdated, very much the same concept. Regardless, I hope you enjoyed learning a little bit about multi-agents and how they work together, and think about it just in terms of how does an agent do what's best for itself? How can it benefit the society of agents, and so on. As always, if you have any questions, let me know. I look forward to speaking with you in the future, and thanks as always for watching.